So the application example, as you can see on your screen, it shows that you have a shaft that is A, B, C, D, this particular shaft, and you have the circular discs attached at A, then B, then C and D, where you're applying the torque. So the whole purpose of the circular discs is that so that you can, apply the torques easily. One way to imagine this, maybe these discs can be gears where you have, some kind of torque that is acting. Okay, from initial perspective, this may seem to you that it is a problem of non-uniform torsion. And why? Because you have a shaft where in different points you have these discontinuities, where discontinuities being the different torques which are being applied. But if you look at individual parts, they are in uniform torsion, and as we will walk through the questions, you will see that it only asks for some of the parameters for these individual parts and not for that entire shaft that you have. So let's go ahead and look at the question. So what it says is that your shaft BC, this particular portion, is hollow and it has an inner diameter of 90 mm and outer diameter of 120. So maybe let's just mark it here that this is a hollow shaft. So this one is hollow, right? Whereas your shafts AB and CD, this one and this one over here are solid. So let's just mark that as well. So this is solid and this one is also solid. Okay, now let's look at the question. So what it says that for the loading shown, so the only type of loading in the entire shaft are these torques which are acting at A, B, C and D, and you are given the magnitudes of that. So for that it asks, first one, the minimum and the maximum shearing stress in BC. So in this part BC over here, what is the minimum shearing stress and what is the maximum shearing stress? Now remember, the minimum here will not be 0 because it is not a solid shaft, right? So BC has an inner diameter and an outer diameter. So at the interface of the inner diameter you will have the minimum shear stress, and at the exterior of the outer diameter you will have the maximum, and at the inner one you will have the minimum, right? So now before we go ahead and start crunching numbers for this problem, first thing, as you know, we always have to do is that we have to check whether our system is in equilibrium. So let's take a look at whether this entire shaft with all these torques applied is in equilibrium or not. Now to test that, let's just draw the overall free body diagram of this one. Now if I am drawing this in 2D, right, and we will also mark the torques in how we are used to represent that in terms of the double arrows, just to make it a little bit easy for us. So we have, this is the shaft that is there. So I have 4 points. I have point A, right, I have a point B over here, right, I have a point C, and in the end I have a point D. Okay. And at all these places, the torques which are acting, so let me mark them by the double arrows. And you also have to be careful about what is going to be the direction. Remember, your fingers must curl about the direction of the moment, and then your thumb will point towards the direction where the double arrow should point, right? So for example, for A, if you see, if you curl your fingers, right, it points towards the axis of the shaft over here. So at A I am going to have a torque, right, which is 6 kilonewton meters. So I'm just going to write the numbers over here because the units are given and I just want to keep the figure a little neat. So 6 kilonewton meter over there, right? Then at B I have a 14 along the same direction that is acting. So I have a 14 over here, and at the point C I have a 26 in the opposite direction. And lastly, at D I have a 6 acting in the same direction as the torques at A and B. Right. So let's see first that whether the system of torques is in equilibrium or not. So all the torques which are maybe pointing like this one is your 6 plus 14 plus 6, and the only torque which is acting in this direction equals to 26, right? So the first one, 14 plus 6 plus 6 is 26. So you see that the system is in equilibrium because the torques which are acting clockwise and the torques which are acting in anti-clockwise, they are sort of equal and opposite, so your system is in equilibrium. So we have established that. So now we can go ahead and solve the problem once we have established that our system is in equilibrium. So now coming to the first part, the minimum and the maximum shearing stress in BC. Now remember, BC is hollow. This is given. BC is hollow and it has an inner and an outer diameter. So maybe let's just try to draw how the section of BC looks like over here. So say, let me just try to make it a circle. Yeah, it's more or less in the center, right? Okay, so what we have, so your inner part is hollow. So this is the hollow core that is there, and it has a inner radius and an outer radius. So let's try to mark those as well. So if this is my center, so I have, oops, sorry, yeah, so I have an inner radius and an outer radius. So let me mark my outer radius is R2 and the inner radius is R1, where as per the question that is given, I know my R2 is 90 divided by 2 because the outer diameter is 90, and your R1 comes out as, oh sorry, the outer diameter is 120, it's not 90, correct that, and R1 is 90 divided by 2. Right. So this may also be a good time to just calculate the value of J, and remember both of these are in mm because your diameters are also given in mm. So this is both in mm over here. So this is also a good time to calculate the J for the section because we are going to use the J for our calculation. So we know that J for this tube is going to be pi over 2 R2 raised to 4 minus R1 raised to 4. Now if you substitute the numbers, I have it calculated over here. This comes out as 13.92 times 10 raised to minus 6 meter raised to 4. You can keep in mm also if you want to substitute everything in mm and newtons eventually. Right. Okay, so now that we have calculated J, so let's calculate the minimum and the maximum shearing stress. Now what we saw in the lecture is that the minimum shearing stress occurs at R1. So at R1 you will have so T minimum, so the tau minimum happens at R1 and tau maximum happens at the outer periphery at R2 over here, right? So we know the formula what we had derived previously. Let's write the most general formula first. The most general formula was your tau equals to T, the applied torque, times rho, which is the radius where you are looking at, divided by J. Right. So from this one you can calculate what is going to be my tau max. It is going to be the applied torque over there, right? So I still have not calculated that. Remember, I still have to calculate what is the torque in that section BC because it asks specifically for BC, meaning maximum and the minimum stress, right? So this is going to be T times the outer radius, that is R2, which is what I've calculated over here, 60 mm, right? Divided by J. So you have to substitute the right units because J I calculated meter raised to 4. So this one you also have to sort of make it into 10 raised to minus 3 in terms of meters, right? Now coming to this guy over here, the torque, right? So what is this? See, this question asks you that about the maximum and the minimum shearing stress in BC in this particular section. So how do we get that? Now as you can clearly tell, we just have to establish the equilibrium over there to find that internal torque which is active. So this T is nothing but the internal torque. So maybe let's just mark it over here that this T is nothing but the internal torque. internal torque at BC, at the section BC. And how do we find that? Very simple. So we come over here, and if we take, say, a section, or in this 2D figure which we established, if we just take a section and if we just draw the free body diagram either to the left or to the right, let's try to draw that one. And see what we get over here. So if I am drawing the free body diagram up to that particular section where I just cut it, so again at the left end I have my 6 kilonewton meter torque which is acting at A, right, and at B over here I have 14 kilonewton meter torque that is acting. So to balance it out, remember this section which I cut, I could have taken anywhere just to the right of B and just to the left of C, right. So here I have, of course, the balancing torque. What I will get over here is is going to be an opposite 20. I have 14 plus 6 over here, so it's going to be opposite 20. So the T, the internal torque there, is 20 kilonewton meter, right. So this tau max is simply going to be equals to 20 times 60 times 10 raised to minus 3 divided by the J, which you just calculated over here. So if you substitute all these numbers, what you will get, and I have this calculated here, so I'm going to write it up. We are going to get our tau max. You can put it in your calculator and you can calculate this. You will get as 86.2 MPa, megapascal, right. And in a similar manner, if I have to calculate my tau minimum, so tau minimum is going to be, remember, tau minimum is happening at the inner diameter, right, which is at R1, at the inner radius, at radius R1 over here. So it is also going to be 20 times, this is the T, torque T over here, right, times the inner radius, that is the 90 divided by 2, so that is 45 into 10 raised to minus 3 divided by J, right. So once you substitute the numbers over here, you are going to get your tau minimum, that comes out as 64.7. So these are the two of the answers, which are the minimum and the maximum shear stress which is happening at that particular cross section, right, minimum and the maximum shear stress in BC. So this is what we have just solved. So I hope this problem was clear. We just found the internal torque which is happening here, and simply we used the formula which we had derived in this particular example, that T equals to tau equals to T times rho divided by J, and with that we calculated the maximum and the minimum torque. So let's go ahead and do the part 2 of the problem. So we are going to start on a clean page for the second part of our problem. I have the same system, and the second part of the problem now asks you that what is the required diameter D of AB and CD if the allowable shearing stress is 65 MPa. So it is giving you the tau allowable and asking you to find the diameter D over here. Now first of all, are they going to be the same? I don't know, maybe if they're subject to the same amount of torque, they will be. And if you closely observe here, you're lucky, because here at A you have a 6 kilonewton meter torque. So if I'm coming and taking a section in this part, right, I will get the internal stresses. If you again do the force balancing as we did in the last problem, or the torque balancing in this case, you will get the internal torque as 6 kilonewton meter. Similarly, if you take a look at this section CD over here, if I'm cutting a section at the point D, you are applying a 6 kilonewton meter. So there also in the CD, the internal torque you are going to get is a 6 kilonewton meter. So maybe it's a good point to maybe make a note of. So let's write. So internal torque at both AB and CD is 6 kilonewton meter. This is an important observation, and that's why we can tell that the final diameter is going to be the same. If those would have been different, then maybe you will get a different diameter D for your AB and a different diameter for your CD. So let's calculate what is the diameter we need. So as we know, again the same formula which we are going to make use of is that we know that our tau equals to T times rho divided by J. This is the generic formula. Now remember that your shaft AB and CD are solid. So both these shafts are solid shafts. So the maximum torque is happening at the periphery, and the minimum torque is 0, which is at the the maximum shear stress is happening at the periphery, and the minimum shear stress is 0 at the center. So for the allowable shear stress, of course, you are going to compare with the maximum which is happening at the periphery. So we are going to write that equation. So your tau max, right, is going to be the internal torque which is occurring at either AB or CD, which we have just calculated as 6 kilonewton over here. So it is going to be 6 times rho to the outside periphery. It is going to be, so let me maybe draw the the cross section over here. So if this is the cross section, what we get, and if this is your center, what we are trying to find is this one, right? So this is your R, which is nothing but d over 2. Remember, the question asks you to calculate d. So what we have, if we come back to this equation, it is going to be d divided by 2, right, divided by j. Now this j, now you have to this is a solid section, so unlike the one which we did previously, so j in this particular case is going to be pi over 2 times d over 2 raised to 4. That is that, in the r raised to 4, r is d over 2. Now here you are going to come and you have to find d. That's your question. And tau max is going to be the maximum shear you are allowing over there. So this tau max is nothing but 65 MPa. You have to do a slight change of units and so on, because here you have put your 16 kilonewton meter. So once you sort of do this, you input the correct units and you do the internal rearrangement, what you and you can calculate this, what you will eventually get, that your d comes out as, please calculate this and then see if you get the same number. I'm pretty sure you will. D comes out as 77.8 mm. Right? So this is the answer for the second part. Okay, so I hope both the parts were clear. One very important thing for both the parts was finding that internal torque, and since this problem looks like a non-uniform problem, but it is actually uniform because you are dealing with individual bits which are in which are experiencing uniform torsion. This problem does not ask you for the the entire deformation or anything along those lines. So I hope this problem example for the uniform torsion was clear.